So we've been talking about the life stages of a star, like our sun or whatever. And today what we want to do is kind of put some more meat on that. Let's talk specifically about how stars form. So kind of like the beginning stages of the life of a star. So, hey, that's where we're going to go today. All right. So it starts with an interstellar gas cloud. Interstellar gas cloud. What does that mean again? That's just a bunch of gases that are in space. So if I've got a bunch of items in space, so if you look at the picture, just a bunch of hydrogens and heliums. And so we have right here an interstellar gas cloud. And so actually the cloud is more kind of through here, sort of this purplish area. And so we have this cloud, and we can see a star kind of in the middle of it. So as things happen, all right, so you've got gas up in space. What do we find about this, the nature of this gas? Well, it's made of hydrogen and helium and others. All right, so hydrogen and helium is 71%, and then everything else is 27%. So it's just like a bunch of dust flying around in space. All right, so it's microscopic particles of silicates, carbons, and iron. So we've got a bunch of different things floating around. And the temperature is actually kind of cold, 10 Kelvin. Not just kind of cold, that's really cold. I mean a really cold. Very, very cold. But then what happens is because of gravity, remember gravity is the key, if I've got particles, they're going to start moving towards each other. Okay? Because everything's attracted to everything else. That's what gravity says. Okay? And then the low temperature leads to low pressure to support the cloud against gravitational collapse. So still, but then the collapse may be triggered by collision with another cloud. So actually, interesting we find when we look at these clouds, the clouds themselves are, let's call them clumpy, because they're not uniform, we would say. Or as I say down here, non-uniformity. They're clumpy. That leads to formation of smaller, warmer, dense. So this, every clump, if there's more stuff, more mass, or let's say more stuff equals a warmer temperature. And so this region right here would be warm. And this region would be warmer. And this would be a cool region right here because there's not as much stuff. Get it? Okay, so we're getting there. Okay. And then eventually they start to rotate. And I don't quite understand why they rotate. I was asking Dr. Boyer the other day, and he's not sure either. But anyways, they do start to rotate. There's probably some physics behind there that we don't know. And so as they begin to rotate, the dense clumps flatten into a disk. And about 1 million years later, you get a small, dense, hot core at the center. Because if you can get more stuff together, remember, more stuff equals higher temperatures. And if you get more stuff, it gets hotter. And more stuff hotter. And more stuff hotter. And more stuff really hot. And eventually, it's hot enough to form a protostar. And then stars generally form in groups in similar ages. So you get a group of stars that will form from these different clumps that we saw back here. This might form into eventually one star, and this will be another star. So we kind of get clumps of stars that are kind of close together. And it creates this thing called a bipolar flow, not that important, but we get kind of a weird shape coming out of here. And eventually, so now let's take a look at a video clip that kind of helps us understand how stars are born.
I don't believe what I just saw!
I know. Wasn't it super?
Super? Ms. Frizzle, DA star is gone! It's history! 650 for nothing!
But why did our star explode when it did? It looked okay on the outside. It was bigger. It was brighter. Well, Horace did say the supergiant was 20 million years old.
A stellar observation, Phoebe. Stars do grow old and eventually go out. But some, like this one, go out with a bang! They're called supernovas.
Wow, it sure left a super mess.
You know, it looks a lot like the place where we found the baby star. All these leftovers from the blast are clouds of dust and gas.
Then let's get out of here! Last time we got too close to a cloud of hot gas, we almost got fried!
But Tim, don't you see? That hot ball of gas was a star getting ready to be born. That's right! Stars are made out of hot gases.
Boingo, Phoebe. Hot gases squeezed together in a ball.
Yeah. Squeezed together hot enough to make a new baby star shine. The hot gas keeps the star shining like fuel for a fire for millions and millions of years. And when the fuel finally runs out, the stars die out. And those that go out with a bang like this one leave behind the stuff to make new stars again.
Excuse me, but in case you've forgotten, we still don't have a present for DA's birthday!
No, but maybe we can make one.
Huh?
As I see it, all we have to do is help along what happens naturally. What if we gather up all the leftover gas and dust and squeeze it together till it gets hot enough to shine?
Brilliant idea, Keisha. Normally it would take 1,000,000 years to clean all this up, but since we do have a magic bus, it's time to take chances, sweep up the mess, and make a star.
Well, actually, before we do that, let's talk about the protostars. That's right, I didn't want to talk about this. All right, what are the characteristics? Well, the temperature of a protostar, okay, is the temperature is about 1,500 Kelvin. Okay, that's a lot better than that's warm. Okay, but it's not warm enough to be lit on fire, so to speak. It's not fused together. We don't have fusion yet. It'll shine in the infrared and the radio wavelengths. So that's, remember on our spectrum, this is a colder than visible light. Okay, so you can't see them with optical telescopes or the Hubble or whatever. You can only see them infrared or radio wavelengths. Okay. But they're a low temperature star. Now 1,500 Kelvin is quite warm from our perspective here on Earth, but for a star that's very cold. Okay, and so it's very difficult to detect these. But we have seen them. For example, so you don't necessarily write this. It's been found in the Book Globule. It's a place up in the sky, and we can see them. So let's just say that they're there. Okay, so I'm not sure you necessarily need to write all this down, but it is kind of interesting. These are some pictures of those. All right. And then the gravity begins to draw the material inwards. So remember, it's starting to they're getting close. The protostar, the atoms are getting closer and closer and closer together. And as they get closer and closer, they begin to collide. And eventually it heats to, yes, that's right, not 1,500 Kelvin, but 7 million, that's with an M, Kelvin in the core. And eventually, when you can get to 7 million, we have fusion take place. Hey, got the music? Hey, doo-doo. And then eventually the collapse of the core ceases, but the protostar continues to acquire material for about 1,000,000 years from the disk. And so it draws all that stuff in. Because now, as it's drawing in, it heats up. And now eventually what happens is we now start getting energy coming out because now we have nuclear fusion, right? That's where, again, the hydrogens are combining with the hydrogens to make helium. And, yeah, so that's how that works. What I need today, you mentioned my rooms. Well, let's just talk about what we call stellar mass limits. Basically, how big can a star be in terms of its mass? Now, remember, we always measure everything compared to our sun. Our sun is one mass unit. They have this little symbol here going on there. But if you get ones that are smaller than about 0.1, they are rarely seen since their masses are too small for their cores to have fusion. There's not enough mass to get fusion to start. So those stars, it's very, very difficult to use a telescope and say, oh, there's one of those 0.1s. Yeah, too hard because they're just too cold. And so they're not producing enough light. And they're not producing enough light, we can't see them, whether it's infrared or whatever, or visible or whatever. Visible we can see it. So that's a limit. We just can't see them. Objects with masses between planets are called brown dwarfs or failed stars, extremely dim and difficult to observe. So it's very difficult to see. That's a typo right there. Okay, now on the other end, what if we were to increase the mass? How big can a star be? Well, the answer is about 30 times the mass of our sun. Because if you get extreme temperatures and luminosity preventing additional material from falling on them, because they produce so much energy that they're actually, they're pushing so much energy out and stuff out that they push things away from it. Okay, and yeah, so kind of the answer is from 0.1 to 1. That's us. And up to about 30. So it's hard to be below this. Not very often. Not very often can you get one above 30. Most of them are between, about 1 and 30. Okay? So, that's a pretty quick podcast. Hopefully you've got all that down.